As you can remember, on our previous lessons, we have found inductance of inductor, and we have found electromotive force of self-induction. It can be expressed by formula. Electromotive force is equal to minus inductance, first derivative of electric current by time, di by dt. Okay, and let's let's have a look and at next simple electric circuit. I will draw a scheme of it, of this circuit. This scheme can be drawn in this way, in this picture. Or maybe resistor, and here we have source of power. Source of power is here. So we have electric circuit that is shown on this picture. Here is inductance. Here is resistance, and source of electromotive force, internal electromotive force. Here we have switcher key, and this switcher can be used to close this part of circuit, or this part of circuit. So we can change different parts of electric circuit by use this switcher key, the switcher key. Yes, and it is necessary not to confuse that this electromotive force and this are different values. It is necessary not to confuse them, because this is some internal electromotive force, and in formula we have electromotive force of self-induction in inductance L. In inductance L. And let's consider that that in first case we have turned a switcher in this way. So this big part of electric circuit is activated by the switcher. What do we have in this case? In this case, if electromotive force, internal electromotive force is constant, we will obtain direct electric current in inductance. Direct electric current, and direct electric current is constant, and derivative from constant is 0. So when we have direct current in this part of circuit, we don't have any electromotive force of self-induction. But what will we have after changing the direction of our switcher, after activating this part of circuit? What will we have in this case? In this case, internal electromotive force will be turned off. And electric current will begin to decrease. But it will not become equal to 0. It will not become equal to 0 rapidly. It will decrease. It will decrease step by step, slowly, and it will take some finite time. And let's calculate work of self-induction in this case. Why do we need this work? And why decreasing of electric current takes time? It happens because when electric current changes in time, electromotive force of self-induction occurs in the circuit, and electromotive force of self-induction, according to Lenz's rule, tries to prevent change in electric current. And because of this change of electric current doesn't happen rapidly, and it takes finite time span. Time span to this. So and electromotive force of self-induction may produce some work, and this work will be spent to heat resistance. So let's calculate this work. maybe you can remember from our previous lessons, when we just started to learn electric current. We have learned that electromotive force can be defined as work divided by electric charge that passes through electric current. And according to this formula, work of electromotive force can be written in this way. So electromotive force of self-induction multiplied by a change of electric charge in electric circuit. We have to use differential here because when this part of circuit is activated, electric current changes. So we have alternate electric current. That means that electric current changes in time. And we can remember from the definition of electric current that it is equal to first derivative of electric charge by time. So we have that it is equal to minus L d I by dt multiplied by I dt dt differential of time vanishes, and we have that this is equal to Li di, and we can calculate whole work of electromotive force of self-induction. We can calculate from here. And we have that this work is equal to integral from 0 to a from 0 to a by dA from 0 to a, and this is equal to integral minus L I d I. And we have to define integral limits. If this part of circuit is activated, electric current changes from its initial value I to zero. So we can find that this is equal to minus. I'll get rid of this minus by changing places of integral limits from 0 to I, and it allows me to write this without minus. So we have I di, and this integral is simple. And it is equal to L I to the power of 2 divided by 2. Okay, do you have any questions? No questions. Okay, and why does this work occur in this case? This work, of course, according to the law of conservation of energy, this work requires some energy. And where does this energy occur? Where is this energy? This energy is in magnetic field. Inside inductance L. This energy is in magnetic field. This energy is in solenoid. So according to this, we can write that magnetic energy of magnetic field in some element with inductance L is equal to L I to the power of 2 divided by 2. We have just proved this formula. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, so I will write this in red frame, that energy of magnetic field energy of magnetic field in an element with inductance L. Energy of magnetic field in an element with inductance L. This energy can be calculated by this formula. Can be calculated by this formula. And what is interesting in this case? It is interesting that that this formula for energy is quite similar to formula for kinetic energy. For kinetic energy of material point, for example. As you can remember from mechanics, kinetic energy of material point is equal to m multiplied by v squared divided by 2, or kinetic energy of rigid body that rotates around a fixed axis is equal to moment of inertia multiplied by angle velocity to the power of 2 divided by 2. And energy of electric field in capacitor. Energy of electric field in capacitor is equal to capacitance multiplied by potential difference divided by 2. So you can see these 4 formulas for different energies, and they all look quite similar. I hope it will help you to understand them, and if it is necessary, to remember. Okay, do you have any questions about this? Do you have any questions? Okay, if there is no questions, let's remember that on our two previous lessons, we have learned and we have obtained two formulas for magnetic induction inside a solenoid. Magnetic induction in solenoid is equal to mu 0 Ni, where N is number of turns divided by length of solenoid, and according to this we have that electric current in solenoid is equal to magnetic induction divided by mu 0 n. Okay, and what about inductance? Inductance of solenoid. We have obtained in our previous lesson. Inductance of perfect solenoid is equal to mu 0 n multiplied n to the power of 2 multiplied by volume, where V is volume inside solenoid. Okay, and let's use these formulas. Let's use this formula here. Let's use them here. We can get from here that energy of magnetic field inside solenoid is equal to mu 0 n to the power of 2 multiplied by volume multiplied by volume and divided by 2 and multiplied by b to the power of 2 divided by mu 0 n in curl brackets to the power of 2. Okay, and after simplifying we have that this is equal to b to the power of 2 divided by 2 mu 0 multiplied by v. Okay, do you have any questions about this? Do you have any questions? No questions. So we have obtained. We can obtain from here. We can obtain energy density of magnetic field. So energy density of magnetic field is equal to W energy of magnetic field divided by volume, and this is equal to b to the power of 2 divided by 2 mu 0 to mu 0. And we can also remember, or maybe you have some questions about this. No. Okay, if there is no questions, let's remember similar formula for electric field. For electric field we have energy density. We have energy density that is equal to electric field intensity multiplied by modulus of electric displacement vector divided by 2. And this is the same as d to the power of 2 divided by 2 epsilon 0 divided by 2 epsilon 0, and this is the same as epsilon 0 electric field intensity to the power of 2 divided by 2. And we can write energy density of magnetic field. In the same way. It will be B multiplied by H divided by 2, and this is the same as B to the power of 2 divided by 2 mu 0, and this is the same as mu 0 h to the power of 2 divided by 2 divided by 2 divided by 2. It is necessary to remember that we can get one formula from other. We can change magnetic induction B to magnetic field intensity and magnetic field intensity to magnetic induction by formula B. B is equal to mu 0 h. This formula allows us to obtain this. Okay, do you have any questions about this? This is energy densities of electric and magnetic field. And sum of these densities is energy density of electromagnetic field. So energy density of electromagnetic field. Energy density of electromagnetic field. This is energy density of electric field plus energy density of magnetic field. And it can be calculated with this formula. So electromagnetic field has energy, and you may meet this energy. You may see this energy, for example, when you use microwave oven or induction cooker. These devices use energy of electromagnetic field to heat food in microwave oven or induction cooker. Or maybe it is necessary to say something about solenoid. We said that we have learned some properties of perfect solenoid. It means that there is no magnetic field outside the solenoid. But if some solenoid or element isn't perfect, isn't perfect. It means that inductance of this element depends on some internal factors, and sometimes it is useful. Sometimes it is useful. Elements with inductance that depends on internal factors can be used in sensor touch screen, can be used in inductive touch screen. These elements can be used. Elements with inductance that depends on some initial factors. And now you know something. You have learned something about inductance, about what is this, about what this is, and about that inductance may depend on initial factors. Okay, and now we have to make some conclusions. We have to make some conclusions about electromagnetism. And after this, we are going to start new topic. So according to knowledge we have learned, we can write Maxwell's equations. Maxwell's equations. Or Maxwell-Heaviside equations. Heaviside equations. In integral form. In integral form. Maxwell-Heaviside equations in integral form. They can be written. In this way. It is necessary to remember. All that we have learned before. The first, we have learned Maxwell-Faraday equation. We have learned this on one of our previous lessons. Maxwell-Faraday equations. Linear integral of electric field is equal to minus surface integral of first derivative of magnetic induction by time, ds. It was Maxwell-Faraday equation. The next Maxwell equation is Ampere's law, Ampere's circuital law. Ampere's circuital law with Maxwell's addition. Ampere's circuital law. This can be written in this way. Linear integral of h dl is equal to surface integral surface integral, electric current density plus derivative of electric displacement vector ds. The next equation is Gauss law or Gauss flux theorem. Gauss flux theorem. Gauss flux theorem. Gauss flux theorem. ds is equal to electric charge density rho. This is charge density. And the last equation is Gauss law for magnetism. Gauss law for magnetism. Gauss law for magnetism. ds is equal to 0. And it is also necessary to add connection between electric field intensity and electric displacement vector. D is equal to epsilon 0 E, and connection between magnetic induction and magnetic field intensity, mu 0 H. And it is also necessary to add Ohm's law in vector form. Electric current density is equal to conductivity, equal to relative conductivity multiplied by electric field intensity. Relative conductivity multiplied by electric field intensity. This is Maxwell's equations or Maxwell-Heaviside equations in integral form. And these equations can also be written in differential form. These equations can also be written in differential form. How to do this? This Maxwell's equations. Or Maxwell-Heaviside equations in differential form. How to write this form? Linear integrals should be replaced. Linear integrals in left sides of equations. Linear integrals should be replaced with rotors. Should be replaced with rotors. So we have rotor E is equal to, and what to do with integral in right side? In right side. Oh, sorry, I have made a bad mistake. I have made a bad mistake. It is necessary to fix this. It is necessary to fix this mistake. Of course, this is equal to triple integral Vs rho d v. Yes, and this will be this will be better. This will be better. This will be better for us. What to do with integrals in right sides of formula? In right parts of formula. Right parts should be written without integrals. So for the first equation, for Maxwell-Faraday equation, we have differential form that can be written in this way. This can be written in this way. Maybe it is necessary to say a few words about rotor. Sometimes instead of rotor you may see another signation. You may see another signation in internet or in books. Carl. So this is another signation, and this is vector product of del operator and E. So this is the same. So because sometimes this can be written in different ways, and it is necessary not to confuse them. Okay, Ampere's circuital law in differential form. Linear integral should be replaced with rotor. Should be replaced with rotor. H. And right part should be written without integral. So we have electric current density plus derivative of electric displacement vector by time. Okay, what about Gauss flux theorem? Surface integral in left part should be replaced with divergence. should be replaced with divergence. Should be replaced with divergence. So we have divergence D. Divergence D is equal to, and in right part we write without integral, is equal to rho, and Gauss flux theorem for magnetism will be divergence of B. Divergence of B is equal to 0. And it is also necessary to add connections between H and B and E and D. So D is equal to epsilon 0 E. B is equal to mu 0 H, and Ohm's law in vector form. In vector form. So this is Maxwell's equation in differential form. Maxwell's equations in differential form. So we have learned them before, but we have learned them separately. And now we have written them together. Okay, what questions do you have about this? Do you have any questions about this? About electromagnetism. Okay, so let's finish learning electromagnetism and start learning mechanical oscillations. Start to learn mechanical oscillations. And the first we will start from the most simple case. The most simple case is free oscillations. Free oscillations without damping and without external force. So without energy decreasing, and without external force. And the first we will have the first we are going to learn simple harmonic oscillator. Simple harmonic oscillator. Simple harmonic oscillator. Simple harmonic oscillator. What is this? I'll try to draw a picture. Let's imagine that we have wall that is connected with spring, constant K. K is spring constant. We have learned this in mechanics. And in this case, and this is mass m. The mass of the spring is infinitely small, and this part has mass m. And it means that there is a tensile force that acts on mass m from the spring. Tensile force is equal to minus k multiplied by x. Minus k multiplied by x. So let's write a differential. Let's build differential equation for this simple harmonic oscillator. So simple harmonic oscillator means that we have only this tensile force, and there are no any other forces, only this force. So according to the second Newton's law of motion, we have that mass multiplied by acceleration is equal to force, according to the second Newton's law of the motion. And let's remember that acceleration. Let's remember from kinematics that we learned in September. Acceleration is the first derivative of velocity, or second derivative of coordinate. Dx second d in dt 2 second derivative. And let's make a substitution. Let's substitute this here, and we obtain from this that mass multiplied by second derivative of coordinate d 2x by dt 2, and this is equal to minus k x x. And let's make some algebraic changes and rewrite this equation in this way. Plus k divided by m x is equal to 0. Okay, and let's write this differential equation in another form. d2x by dt 2 by dt 2 plus omega 0 x is equal to 0. So this can be written can be obtained from mechanics. And what is omega 0? Omega 0 in this case is equal to square root of spring constant divided by mass, and this is natural frequency. Natural frequency. This is natural frequency. This is natural frequency. And what about what about period? But we still don't know that this is a period, but we will prove this on our next lesson. We will prove that this is frequency and period. So period is double P divided by mega 0, and this is the same as in this case 2P square root of m divided by k, mass divided by the spring constant. So this is period of oscillations. Period of oscillations. I'll move this here. Is period of oscillations. Period of oscillations or free oscillations. Period of free oscillations. Okay, period of free oscillations. Period of free oscillations. Okay, do you have any questions about this? Do you have any questions about this?
No.
No. Okay. No questions. So we have obtained that for simple harmonic oscillator, we have obtained differential equation of free oscillations in this oscillator, and we have obtained natural frequency and a period of free oscillations. Later we will solve this equation. We will solve this equation, but now it is necessary. It is necessary to learn some other systems with oscillation. The next system is a torsional pendulum. Torsional pendulum. Torsional pendulum. So what is this? What is this? Imagine that we have quite thin rod, quite thin rod that is fixed in cylinder. So here this rod is fixed, and and the lower part of this rod is connected with disk that has moment of inertia I, and rod has parameter D. What is D? D is a torsional constant. D is torsional constant. Torsional constant. D is torsional constant. It is very similar. It is very similar to spring constant. It is very similar to spring constant of harmonic oscillator that we have learned before. So torsional constant is very similar. It means that moment of force or torque that is impressed on disk is equal to minus d multiplied by phi. Minus d multiplied by phi. Where phi is angle of rotation. Phi is angle of rotation. And let's remember the equation of rotational motion dynamics. This equation can be written in this way: moment of inertia multiplied by angular acceleration, and this is equal to moment of force. This is equal to moment of force, where angular acceleration is first derivative of angular velocity divided by time, first derivative of angular velocity, or second derivative of angle of rotation. So let's substitute this here. So we have that this is equal to moment of inertia multiplied by second derivative of angle of rotation, and this is equal to minus torsional constant multiplied by angle of rotation. So we have obtained a differential equation for torsional pendulum. And we can make some algebraic actions in this case. D2 phi by d t to 2 plus d divided by I phi equal to 0, and from this we have that d2 phi by d by dt 2 plus omega 0 phi is equal to 0, where omega 0 is natural velocity or natural frequency, and this is equal to square root of d divided by moment of inertia, torsional constant divided by moment of inertia, and period of free oscillations is equal to 2p divided by omega 0, and this is equal to 2p square root I and I moment of inertia divided by torsional constant. Okay, do you have any questions? Do you have any questions about torsional pendulum? No questions. Okay, so we have obtained that this is equal to and natural frequency and period of free oscillations. In this case. So the oscillations are rotational. These are rotational oscillations. So angle of rotation changes from left to right. In this case. What is necessary to notice in this case? What is necessary to notice in this case? As you can see, differential equations for these two different systems, differential equations are very similar. Linear homogeneous differential equations, simple differential equations of second order. So differential equations in these two cases are very similar. Okay, so let's have a look at one more system, oscillation system, physical pendulum. What is this? I'll try to draw this. So here we have this is vertical line. I'll draw this in dash as vertical line. And here we have here we have some rigid body that this axis axis z that is perpendicular to the screen and is directed from the screen to us. Axis z is directed from screen to us. And here, this axis is here. This axis is here, and the center of mass of this rigid body is here, for example. The center of mass is here. The center of mass is here. Mg is gravity force, and we can write that radius vector from axis of rotation to the center of mass is r. This radius vector is r. This radius vector is r. Maybe I'll rewrite this. I'll make it a little bit bigger. This is radius vector from axis of rotation to the center of mass of rigid body with mass m. With mass m and moment of inertia I. In this case, we also have differential equation of rotational motion dynamics. We know it from mechanics. Moment of inertia multiplied by angular velocity is equal to moment of force. And beta, you can remember that this is the first derivative of angular velocity by time, and this is equal to second derivative of angle of rotation by time. Okay, and what about moment of force? This is the angle of rotation phi. What about moment of force? We have learned it from mechanics. Moment of force in this case is moment of force in relation to the axis of rotation. So we have that this is equal to minus r multiplied by mg, that is perpendicular to the part of mg or projection of mg on the direction that is perpendicular to axis z and vector r. and vector r. So it means projection of mg on this direction. Projection of mg on this direction. So here we have we also have angle phi. So we have to find projection of mg on this direction. This will be mg perpendicular. This will be mg perpendicular. This will be mg perpendicular. And according to this, we have that this is minus mg r sinus phi. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. Okay. Okay, if there is no questions, so I will clean something from this picture. I will clean it from this picture and let's make substitution. Let's make a substitution and we can obtain that moment of inertia multiplied by second derivative of angle of rotation by time and this is equal to minus m g, where g is acceleration of free fall, multiplied by sinus phi. We have obtained the differential equation for a physical pendulum. It is necessary to write this. This is a physical pendulum. Physical pendulum. This differential equation can be solved, but this requires elliptic integral. But as you can remember from calculus, if the angle phi is small, it can be written that sinus phi is approximately equal to phi. So this is approximately equal to minus m g r phi. Minus mg r phi. Okay, but it is necessary to remember that for using this formula, if you use this formula, angle phi must be in radians, not in degrees, in radians only. In radians only. For angles in degrees, this formula doesn't work. Doesn't work. Okay, do you have any questions about this? No questions. No questions. Okay. Okay, so if there's no questions, I can write differential equation for physical pendulum. D2 phi by d t2 plus m g r mgr divided by moment of inertia of physical pendulum multiplied by angle of rotation, and this is equal to 0. And according to this, natural frequency is equal to mgr divided by moment of inertia, square root, and period of free oscillations. Period of free oscillations is equal to 2p divided by natural frequency, and this is equal to 2p square root of I divided by mgr. This is for physical pendulum. Okay, do you have any questions? No questions. No, if there is no questions, let's clean my screen. Let's clean the screen, and we have natural frequency and the period of free oscillations. Period of free oscillations for physical pendulum, and you can see that differential equation is very similar again. Differential equation is very similar again. So it is necessary to change. It is necessary to write this omega 0. Or in this case, omega 0 to the power of 2. Sorry, I have made a mistake. Omega 0 to the power of 2, of course. Omega 0 to the power of 2, and in previous case it was necessary to write also d2x by dt plus omega 0 to the power of 2, omega 0 to the power of 2 multiplied by not phi x is equal to 0. In previous case, it is also necessary to write omega 0 to the power of 2. Okay, what questions do you have? No questions. Okay, and the last for today. The last for today is mathematical pendulum or simple pendulum. Mathematical or simple pendulum. Or simple pendulum. The situation is very similar, similar to previous, case, but instead of rigid body, we have just one material point that is connected by thread of length L, material point of mass m, here we have mg, angle of rotation phi. So of course we have the same differential equation, d2 phi by dt dt2 plus omega 0 to the power of 2 phi equal to 0. But in this case we have that instead of r we have length of the thread L, and moment of inertia of just one material point is simple to obtain. It is equal to mass multiplied by its distance from the angle of rotation. So in case of mathematical pendulum, we can obtain from previous case that natural frequency is mg r divided by moment of inertia, and this is equal to mg L divided by m L to the power of 2. And this is equal to square root of g divided by L. So we have natural frequency in this case. Natural frequency that square root of G divided by L. And the period of free oscillations 2p divided by omega 0, and this is equal to 2p multiplied by square root of L divided by G. The last formula you may remember from the school, from school, maybe not. Okay, so do you have any questions? Do you have any questions about mechanical oscillations? No questions? Okay, let's suggest that there is no questions. So thank you for your attention. Thank you for your attention. I hope to meet you next week. Next week we will continue, and next week we will solve differential equations, equation of free oscillations. Okay?
Okay, teacher.
Okay.
Okay.
Have a nice day.